Hello, I'm Jacob Marcelo. I'm part of Team 7. My coworkers Emmanuel Carderas and Philip King and I will be talking to you about BlackBird, a threat profiling honeypot and traffic analysis tool that is focused on services commonly run on IoT devices. The topics that will be covered include what motivated us to explore this topic and create the tool, an explanation of our abstract and the frameworks that the tool is built on, our contributions to this field of research, and the results generated by the tool we've created. So Internet of Things devices are IP-enabled devices that have been prepped to be able to communicate on the internet. These devices have revolutionized how people live and interact with their environment at home, in the manufacturing industry, and all over the world. Unfortunately, due to many of these smart devices being built with little security in mind, a large number of IoT devices are vulnerable to a variety of different threats and attacks. As a result, many IoT appliances that face the internet tend to be enslaved to a botnet or otherwise compromised by malware. The metrics and insight into malicious traffic gained by advanced threat analysis, profiling, and capturing a wide collection of different attack traffic is what motivated us to implement an IoT honeypot and service emulation system. So to be able to suitably secure IoT devices, it is necessary to understand the entire scope of attack surfaces, vulnerabilities, exploits, and target information that might be part of modern cyber attacks on these types of devices. So essentially, this is what the abstract states, that the tool was created with this objective at the forefront of our design. The tool uses IoT service emulation to provide the user with a safe attack surface. The tool will allow attacks to take place and collect the traffic itself, which will then be analyzed to provide information about the traffic's origin. The nature of the attack and which actors behind the attack is also included. We created an integrated web interface so that the results of the traffic analysis can then be parsed by user-defined variables. We also implemented API calls to gather information from sources such as Shodan and CVEs based on the traffic so that the user can be made aware of vulnerabilities and potential exploits to their services. We then packed and published the tools online on GitHub so that others can freely download, use, and contribute to the tool's progress. The IoT service emulation framework is built using the Keiko framework. So this framework allows the users to host a number of common vulnerable IoT services and can be used to catalog the origins of attacks and collect the body and payload of the packet. Through a number of service simulations that can be configured by the user, it collects data when it is accessed and provides the user with a JSON output file that contains deep packet data that can be further analyzed. So we were able to successfully emulate many common IoT services with vulnerabilities in AWS instances. Some of the hosted services include Telnet, HTTP, and HTTPS for router configuration pages, and UPnP. Our project Blackbird is a fork of the Keiko framework that feeds the generated traffic through our parsing and analysis code so that in-depth information about the traffic can be generated and viewed in an easy-to-access web interface. The user will be able to sort through detailed information about CVE's source, origin, and other information based on our analysis of the traffic. The entire setup is available on a GitHub page that we created, and it'll be shown and reviewed later in the presentation. I'll now pass you to Emmanuel and Philip for further project contributions and an in-depth look into how the tool works and the results that it can generate.
Hello, I am Emmanuel Carderas, and I will now be discussing the potential contributions BlackBird will hopefully have on the cybersecurity research field of IoT devices. Our project was built with the intention of being usable by cybersecurity researchers and other specialists in the field of IoT security research, namely being able to examine malicious traffic and payload hostile actors utilize on unprotected IoT devices and how better to protect your IoT devices from these attacks as a result. For educational research purposes, BlackBird can be used to facilitate research quite easily as IoT devices are vulnerable to a plethora of attacks, thus allowing cybersecurity researchers, both professional and students alike, to make use of the honeypot in order to better understand what is targeted and exploited by attackers, the demographics of the attacks, and other statistical measures to help better understand the nature of these attacks. BlackBird, which utilizes the Keiko framework, will be able to examine the packet data being intercepted by malicious attackers on the honeypot ports, which includes data such as the full packet headers and its payload. The headers include like source, destination, IP addresses, and as long with port and source and destination ports as well. This will allow This will allow BlackBird to perform lookups on the origin of the attacker, such as domain lookups, whether or not a domain belongs to a specific APT or not, for example, and the potential of blocking these malicious entities from further causing harm to the system via an integrated IPS, or at the very least, generating alerts through a built-in IDS. For detailed exploit analysis, BlackBird uses many online APIs in order to examine traffic entering its Honeypot system. For example, it uses Shodan in order to perform analysis on packet data for any suspicious strings or payloads attackers may be attempting to utilize in order to gain access to the system. Another API it will utilize is a CVE lookup in order to identify and return CVE related data in a cohesive and readable format for the user. And last but not least, our collaboration effort for our GitHub project, which I will now take us over to briefly show what it is. So as you can see, it is a fork of the original Keiko framework. And as it is an open source project, we hope that other users will eventually contribute to the project in a meaningful manner. And hopefully this project may grow into an easy to use, simple, open source IoT emulation platform that cybersecurity researchers may utilize without having to worry about a paywall or to build their own from scratch. I will now hand off the rest of the presentation to Phil.
Hey guys, today I'm going to be talking about our results. These are available on GitHub. First, I'm going to recap our previous semester's findings. We used Keiko to capture packets which were trying to access our emulated services. We then used the geolocation service to geolocate the sources of the packets. We visualize this here with a module in Python. Unfortunately, in the environment that I'm recording this in, does not have all the necessary imports, so this screenshot will have to suffice. We also organize the data among most active IPs and most active countries here. Very interesting stuff. Information Keiko gathers from packets were primarily source IP, source port, and payload. It doesn't come with the magic boolean for determining which packets are malicious. We wanted to come up with a way to more accurately determine which packets are malicious. We decided that the Shodan API would be our tool of choice. We found that the Shodan API does not respond well to excessive data. Adding characters around keyboards which would have it return information on will have it return nothing instead. So, we use this algorithm to break up our payloads to be a bit more bite-sized by Shodan. Break up the payloads by line and by space. Shodan does have a free tier, and we wanted to remain within it. So we ran a check to see how many queries the affirmation technique would send to Shodan, and due to Shodan having a 1 query per second policy, how long the process would take. We found that if we did this inefficiently, we would end up querying Shodan over 70,000 times, and this would take over 20 hours. Luckily, by the time we got to the final iteration of our algorithm, once it's been optimized, we got it down to under 20 minutes and less than 12,000 queries. Another problem we faced was Shodan returns a lot of data. We found that if we just stored all the information Shodan returned, it would easily multiply our data size by over 1,000 times, from 3 megabytes to well over 3 gigabytes. Instead, we parse Shodan's response and only keep CVE names, which we store for later. Even this much more minimalistic approach got us from 3 megabytes to over 46 megabytes. We also found that over 99% of our packets contain something that triggered Shodan's API. We are unsure if this is appropriate, because although this is a honeypot with vulnerable looking ports that would likely be attacked frequently, over 99% is a lot. Here is a packet that contains a malicious payload which attempts to run shell commands. This small payload got Shodan to return over 313 CVEs. Here's a little bit of a more palatable example. A bit narrower. If we are just looking at the response that this string would get, slash php myadmin slash php myadmin slash index.php. This is how the response would look. And keep in mind that all this data is just with the CVE names. For those of you interested, if you want to see the total response from Shodan, not after we parsed it, if we query with the same string we did before, it is all of this information. Thanks for watching our presentation.